So last time we did a linear control, so we linearized the system. We assume that this theta is less than equal 6 degrees. It's a small angle, and so we can approximate cosine theta by 1, sine theta by theta, and anywhere you see a large a term that has all of these several terms, you can approximate it by 0. And that makes our equations extremely simple. But of course, it's only going to work when your theta is small, and we could, in the previous example, you saw that I can move it from one point to another point, the cart, while basically bringing this pendulum also back to upright position. Now, when this assumption is not valid, when the angle is not small, then those linearizations and the method that we use, the control method, they are all going to fail. Why? Because we cannot approximate sine and cosine theta. Our ODEs are nonlinear, as you can see. And so control of this system cannot be done using that method that we saw last time. So what do we do? Here, I still write the system into a matrix format, and I want to find the double dot terms. So I factor out the double dot terms and their coefficient matrix of that. Everything else I take to the right-hand side. And then if I multiply the inverse of this, if I call this A and if I call this B, the solution to this double dots is A inverse times B. And what is that solution gonna be? Well, let me show you. So the solution for x double dot is basically this whole term here plus this term times u. That is your x double dot. And similarly, this term here plus that term times u again is what is basically theta double dot. Okay, so these are the solutions for x double dot and theta double dot. If you want, you can replace the notes in my previous video that I said they changed. They're gonna be these guys. So if you do that, now one thing you can do is to take this system into the state space, and you can use 4 states that we used in the previous video, or you can change the order. Initially, I had them, as you saw in the video, as theta theta dot x and x dot, but then I decided to change them and go with x x dot theta theta dot. So it is the same as my previous video. If you call these x1 to x4, then vector x, which is basically x1 all the way to x4, right? This vector here, you can write its first derivative, x dot, as some nonlinear function f of x plus another nonlinear function g of x times u, which is the input to the system. And if that's the case, then your f of x is going to be this one that you can see down here. Let me clean it up so you can see it better. F of x is this first 4x1 matrix, and g of x is the second 4x1 matrix. Okay, so this is going to be your state space equations, this equation 1 basically. Now, the goal is what? The goal is what kind of u should we choose such that this vector x goes to what? Goes to some desired x. That's the goal of what? The control design here. Okay, how do we do that? Well, here we use the method called feedback linearization, which is basically using nonlinear terms in u, which are the same as the nonlinear terms that I can see here for theta double dot and x double dot, and canceling these positive terms with negative and negative terms with positives. So at the end of the day, the governing equation of the system with the u that we applied instead of this nonlinear equation 1 turns out to be a linear set of equations which we can easily control. Okay, so we basically use the negative of the terms that we have in f and g to cancel these nonlinearities, and that is called input-output, or in general input-output linearization or feedback linearization. Now, one thing we have to pay attention to is, although you have 2 degrees of freedom in the system, you only have one control signal U. Okay, you only have one control signal U. You don't also have a torque here. You don't have that, unfortunately. So you cannot really drive this X to the desired X and keep this theta, or derive it to the desired theta at the same time. It's not possible, okay? You have to focus on one of them. Either keep the pendulum or drive it to a desired angle and not caring about X, or care about X and not care about theta. Most of the time you want this pendulum to be held in balance, so you want this theta desired to be 0. So you want to apply a force to balance this pendulum on the cart and keep it in this upright position. That's most of the time what you want to do with the pendulum. But sometimes, no, really, this angle might not be of interest. You want to move this cart to a desired position, okay? So you have to keep in mind you can only go for one of them because you only have one control signal here. And I'll show you how to do for both of the scenarios. So first, let's say we want to focus on theta. We care about theta, which in this case is x3. So the output of the system is really x3, as you can see, and you can call it h of x. So in general, this y could be even a nonlinear function of the state variables. In this case, it's linear, but not always. This h also, like f and g, which are nonlinear, this h can also be nonlinear, but in this case, it's the only thing we care about is theta, so it's a linear combination of the states. Now, one important thing that we need to have if we want to do this feedback linearization method for theta is, or for x, is because the terms we need in this u involve theta and theta dot. So the terms we have for u, for either scenario controlling theta or x, they both involve knowing the values of theta and theta dot. How can you do that? Right? How can you know the angle of the pendulum and its angular velocity at any point? The only way is to have an encoder here. If you have a sensor, if you have an encoder that gives you the angle theta, and if it has velocity feedback, so it also gives you theta dot, then you can have what? You can have reliable estimates of these two parameters. And so, because you have them, and if they are a little bit noisy, you can filter them. If you have good estimates of theta and theta dot, you can form those nonlinear terms that are that you can see in f and in g. You can form these terms and you can cancel them. Okay? So what would you do here for u? This u is to control what? In this case, to control theta. Okay, so right now we want to focus on theta. What do we do? Here we'll look at the governing equation for theta double dot. What is theta double dot? If you remember, I said that theta double dot is what? It is this guy here plus this term times u. This is equal to theta double dot. So what can I do to get rid of these big nonlinear terms on the both sides of u? Well, one thing I can do is, if I pick u to be reciprocal of this term in g, if I make it to be reciprocal of that, so mc plus m sine squared theta L comes to numerator, right? And then what? That other term, which is negative cosine theta, if it comes to the denominator. If u is this, then what happens is when I multiply u by that, guess what? if my, because this theta here is the theta of the encoder really. Okay, this is not the actual theta. This is theta of encoder that I choose for u. And if this theta of encoder is a very good approximation of the actual theta, then this term, when multiplied by u, would cancel each other. So this whole thing becomes simply 1. You see, I could get rid of the nonlinear term in G by selecting the reciprocal of that term in G. I can get rid of it. But how do I get rid of this huge term here? Well, the way you do it is you say u is not just this, it's this one, right? So when you multiply it by that, this times what? Now you bring this extra term and say, well, this is that reciprocal that I showed you. This is multiplied by a bracket. What goes in the bracket? The first term in the bracket, which is this guy, this is exactly the negative of this one here in the F. So now, since there is an addition, I want to add a subtraction. I add a negative. So when this term comes out with this term, they cancel each other. So your theta double dot becomes, in this case, what? 0. But I don't want theta double dot equal to 0. So what do? I add some extra terms to it. What are these terms? These terms are k1 error in theta plus k2 error in theta dot, or a time derivative of error in theta plus theta desired double dot, where error in theta is defined as theta desired minus theta. This theta desired could be a constant number, like in this case we said it is 0, or it could be a variable thing. Okay, so in general you don't need to do a point tracking and drive it directly to a fixed point. You can do general tracking. So this theta of d can be a function of time, but in this case we just want it to be 0. So we use that. Now if I plug this u, which is defined by equation 2, if I plug this u into equation 1, guess what happens? First, u is multiplied by reciprocal of this. So the result of u times g, right, what happens? It just becomes 1. Then this term inside bracket comes out 1 times this. This term now, as I said, will be canceled by this term in what? In F. So your theta double dot will be equal to this rest of it. So this is the result. And as you can see, this is clearly a linear system, right? This is absolutely a linear system. There is no nonlinearity in it. And if I bring this theta double dots to the other side, theta d double dot minus theta double dot will become what? Error theta double dot. So you get what? You get error theta double dot plus k2 error theta dot plus k1 error theta equals 0. And if I choose my k1 and k2 appropriately, there is a guarantee that I can drive e theta to what? To 0. So I can drive theta in this case to 0, or actually it's better to say e theta to 0, not theta to 0. Okay, so here I fixed it. Now, what kind of k1 and k2 I can choose so I can guarantee that this error always exponentially goes to 0? If you find the corresponding characteristic equation for this, it is going to be s squared plus k2s plus k1 equals 0. And if I have this to be equivalent to basically s plus omega equals s squared equals 0, then I can sure that both roots are going to be equal to some negative omega, right? So we just need to select some negative omega. This omega here is a negative number, and if that's the case, this is equivalent to s squared plus 2 omega s plus omega squared, then you can see that your k1 should be omega squared and your k2 should be 2 omega. And that is exactly what you can see over here and over here. So you pick any omega that you want, which determines the speed of the convergence, because when it goes to 0, this error is going to be like e to the negative omega t times some initial value. And this e is different than error. Okay, this is the exponential. So this omega is the speed of convergence. The bigger the omega, the bigger in this case, since it's negative, you can have positive omega, because omega itself is negative. So the bigger negative number it is, magnitude, that errors will converge to 0 faster. So that's how you pick your gains k1 and k2 for some negative omega, and that guarantees the error of theta will go to 0. Similarly, if you have your x as the desired variable, so it's going to be 1, 0, 0 times x in this case, then you do exactly similar thing to last time, except what? This time the equation that you use is the second equation. So this time it is going to be this term plus u times this term is equal to x double dot. So you make sure that you take reciprocal of this guy, and then inside the bracket you have negative of this first term plus those other linear terms. And that's exactly what you have over here. This is that reciprocal of the term in the G. This is negative of that term that you had in F, right? And then what? You have this extra terms here, okay? And again, that will lead to, in this case, ex double dot plus k2 ex dot plus k1 equals 0. And again, if you select k1 and k2, like I told you before, again, your e of x will definitely converge to 0, which means your x will converge to x desired, okay? So you either use equation 2 for control if you want to control angle, or you choose equation 3 if you want to control what? The position of the... Now here I made you a Simulink demo so you can see it, and here my goal is to control theta. I want to keep the pendulum in balance upright. I don't care too much about x, okay? And what kind of signal do I use? As I said, it is going to be this equation 2. So here I have two subsystems. One is the controller, the other one is the pendulum system, the inverted on the cart. And here you see the U goes into the system, and the outputs are going to be x double dot and theta double dot, which they are integrated twice to give you x dot and x, theta dot and theta. The initial condition for x dot, theta dot goes here. This is x dot, so here I start at 0 velocity for both, so the system starts from rest and from position 0, but your initial angle is not 0. If you look here, I made it negative 60 degrees. Okay, this angle is too big that the linear system, the linear control will not work on that. If the pendulum goes to negative 60 degrees and you wanted to apply the same U as in my previous video, it will never bring it back to 0. So here you definitely have to use this feedback linearization method. And what you do here, you can see these are the parameters of my system as used in the previous example, in the previous video. I formed the A matrix, I formed the B matrix, which I call right-hand side here. I multiply inverse of A by B to get my two double dots, and then the first element is x double dot, x2 dot, and the second element is what? Theta 2 dot or theta double dot. Okay, and then by double integrating, I can get x, I can get theta and theta dot. By the way, this theta and theta dot of the system, I need to fit them back into the controller, and it's the controller that uses those estimates of theta and theta dot and gives me what? Gives me the U signal. Now, in reality, here there should be what? There should be an encoder here. An encoder has dynamics. So if I want to invert this, I have to say there is some encoder with velocity feedback, and that one is gonna receive what? This theta and theta dot of physical system and give you some estimates of theta and theta dot, okay? So in reality, theta and theta dot come in, and then estimate of them will go out, or measurements of them will go out. Let's not call them estimate, maybe call them measured, okay? And in reality, it's not a one-to-one wire. There is some dynamics here. That encoder has some errors, it has some noise and so on. So your measured values are not going to be exactly the equivalent of the actual values, right? So that is how you should be doing it. So instead of this theta dot directly going to the controller, it is measured by the encoder, and the measurement value is going to go to, well, seems like I did the wrong wire, so that's the theta, right? And let me bring this guy down. So this theta, when it goes in, this theta measure goes here, and this theta dot measure of this encoder is a measurement of the physical theta. Okay, so it's something like this. Now again, here I made it such that what? I made it such that the encoder has no dynamics, but that's not the reality. You know that there is always problems here. So here I add something and I say no dynamics here, right? No sensor dynamics here. But you can add your own and make the system more interesting. And if you look at the controller, you see that theta and theta dot come in, and U is exactly calculated here based on that equation 2 that I showed you. And these are the gains, of course, with a negative sign. And the reason is here I'm using theta and theta dot instead of E theta and E theta dot. Okay, if you want, you can have E theta and E theta dot. And remember, you also had another term, theta d double dot, but remember that your theta d double dot is 0 in this case. I just want to drive the system to 0 angle. So not only this guy is 0, this theta d is 0 and theta dot d 0. So E theta will be negative theta and E theta dot will be negative theta dot. So I combine that negative K1 and K2 into, instead of 4 and 4, I made them like negative 4, okay? And if I run this physical system for you here, let's go ahead and run it. And you can see that your theta does actually go to 0. Okay, here we go. You see it is exponentially from negative 60. I can control it to go directly to what? To 0. And you can also see theta dot also goes to 0 as well. So you see, initially I get some initial theta dot, and then exponentially it goes to what after 3 or 4 seconds. So my system will go to 0 angle and stays there, but X is not under my control. You can see that X during these 10 seconds has already moved negative 120. Okay, so X is out of your control. It's only theta that you control, and if you want to see the control signal, this is how the control signal does change versus time. Okay, so you see it's a negative motion, and the reason is my initial angle was negative, so I have to move to the left to compensate for that. Okay, so this is a simple demo. As I said, feel free to add noise here or anything that you want. And let's see if I can invert these guys. There we go. That is more reasonable. And feel free to play with this and make it more interesting. So this encoder that I have here is just empty box, but you can make it as interesting as you want. Thank you so much for your attention, and I will see you in the next video. Thank you.